So to start out, I want to take a look at assignments here. Oh, and I've got the wrong chapter there. You should be reading 4.1 to 4.3. We are now in chapter 4. And we've got some assignments, like with every chapter, we've got to prepare to learn. That covers the first half of the chapter. And I'd like you to look at that for tomorrow night, just 3 questions. You are welcome to have open your OpenStax and your overview page to help you with that. You can take it as many times as you like until you get the right answers. Vocab 4 is, I think, due Sunday. If it's due earlier than that, just let me know and I'll change the due date. If it's due after that, we'll go with that due date. And then I may not have given it a due date, in which case I will make it due Sunday. And then you have 2 homework assignments on active chemistry, homeworks 10 and 11. And let me just take a quick look. Homework. Let's see, 10, we are going to be talking about balancing equations today, and then 11 is on types of reactions, which you're working on in lab, but we'll talk a little bit about that today and a little bit about that on Friday. So you have a little bit of time to do those. Any questions? All right. I have started looking at the tests. Sorry, this mask is a little small. And the first page looks pretty good, but I haven't got any farther than the first page. So, you know, hopefully it continues. Some of you may have noticed on Canvas, I have posted an assignment for extra credit. And I didn't really say anything about it. So you might remember I had these things available for doing the isotope symbols. And I said you could take one if you wanted. And I still have a few left over. I'm going to have some of those throughout the semester. If you do those, put them together at the end of the semester, turn them in, and I will give you 1 extra credit point for each thing that you do. So potentially you could get up to 25 extra credit points on every kind of extra credit that you do. Each extra credit point is essentially 1 test point. So if you did 25 of these, that could take you from a 75 to 100 on one of your exams. So, so that's something to think about. So the ones that I have up here right now, this one is on significant figures. So if that's something that you're struggling with, it's a color by number. This is also a color by number. There are 2 versions in here, and this one is on the charges of ions. So if you're having trouble remembering what charge goes with an ion, or what the, I guess it doesn't really do names, but if you're having trouble remembering the charges, this would be good. Or if you just want extra credit. So those are available to you if you so choose. And then I will have other ones in upcoming lessons. All right, I would like for you to pull out your polyatomic ion sheet that we've been looking at. So first thing that I want to look at is the non-bold ions. So the ones that I care most about are the ones that have a very similar ion that is bold. So the bold one would be something 8. Underneath it, there may be something that says ite. So what is the difference between an 8 and an ite based on what you're observing?
8 has 3 oxygens.
Sometimes it has 3 oxygens.
It's more oxygen.
It has more oxygens, okay? What about the charge? If you look at several different pairs.
Same charge.
that has the same charge. So one of the ions on your sheet that I believe it's bold is MnO4. This is something we use in lab quite a bit. This is a good one to know a little bit about. It's very, very, very dark purple. And so it's very distinctive from other chemicals because we very rarely have chemicals that are that dark. If you get it on your skin, it'll turn your skin darker because it's an oxidizer, so it's oxidizing your skin. And it's an oxidizing agent, so it can be used in oxidizing reactions. Okay, if I were to have, let's see, this was a bad example. We'll come back to this one in just a second. Okay, we have ClO4 minus. Okay, this one is what? Perchlorate. So this is permanganate perchlorate. Okay, very similar to one another. Perchlorate actually has 4 versions. We follow the same rule on the charge. It's the same charge. And each time we have 1 fewer oxygen. But we can't just do 8 versus 8 to distinguish between them. So the top 2 are 8 and the bottom 2 are 8. Right? How do we tell the difference between these two? The per. So per is like, think of super, okay? So it's super. It's got extra. So we have perchlorate, then chlorate, then chlorite. And then what about the last one? How do we tell the difference between the bottom 2? You got the sheet in front of you. What's the bottom one called? Hypo. So like a hypodermic needle goes below your skin. Hypo means below. If you have hypothermia, you are very, very cold. Your body is losing heat. Your body temperature is dropping. So hypo is what's used for the very bottom. So that's how we distinguish those. Do we follow the same pattern if we substitute bromine here? So bromine's right underneath chlorine on your sheet.
Yeah.
Yeah. Okay, so once you figure this out for chlorine, it works fine for bromine, right? Okay, so this chemical is not a common ion, but it also exists. This one, oops, this should be an R, sorry. This one is manganate, okay? So what should I call this? Manganite, okay? So the difference between 8 and 8 is just dropping 1 oxygen. And then if I have 4 different versions, and the only place that applies for memorization purposes are for the halogens, chlorine, bromine, and iodine, then we have to add the prefix, okay? So what I want to look at next is the acids. Now the acids kind of line up with the ions. So if you look to the side of perchlorate, we have HClO4. And actually looking at the acids are on the right side, hand side of the page. What do you notice about the acids in general?
Neutral.
They are neutral, okay? So all of our ions have a charge with them. Acids are neutral. Okay, what else? They all have hydrogen. So in every case, the difference between the name and, between the ion and the acid is going to be the addition of a hydrogen. Okay, so hydrogen is kind of our way of identifying acids. Now, technically, there are some acids that don't involve hydrogen, and you'll learn more about them later. But for our purposes, hydrogen, acid, acid, hydrogen. Okay. Okay, so they all have hydrogen. What's the difference between the names for the ion and the acid? So first of all, what's the name of this? Really, just look at paper. This is, oops, I can spell, which I can. Chloric acid. So we kept the prefix, we kept the middle part, the chlor, but this changed and we tacked on acid. Okay. Now, would it be fair to assume that for acids, you would change the ending ate to ic? Check out the other acids on your paper. Does that seem to be a pretty good rule? Okay, you're shaking your head no. What's the difference? What's an exception?
Some of them don't.
Okay, does the ion end in ate if it doesn't end in ic? So what's an example of an ion that ends in ate, but the acid doesn't end in ic? Okay, so are there exceptions that you see? No, okay. But you did notice not all acids end in ic, which is very important. Okay, so most of the acids we use in lab are going to end in ic, but not all the time. So those non-bold ions that have ite, they don't end in ic. What do they end in?
Us.
Us.
OUS.
OUS. Okay. So if you know the bold ions, you can get to the non-bold ions. If you know the bold ions, you can get to the acids. And they all end in the word acid. Okay, there are some acids, and you use some in lab, you'll use some next week in lab, that don't have polyatomic ions, okay? So let me go back over here and erase this a little bit. Okay, there are 3 types of acids. So we have what we call oxoacids. What element do you think is in oxoacids besides hydrogen? Oxygen, that's pretty obvious. So they're going to have the basic formula H and some number. It might be 1, it might be 2, some element, and then O. Okay, so for example, HClO4. So that's an oxoacid. They have the form of anion name changed to either it or us, and then acid. That's just how we name it. They're pretty easy. Then we have what are called binary acids. Binary, bi means 2. So they have 2 elements, one of which has to be hydrogen. So it's hydrogen and something else. So HNXN. So the one we use all the time in lab is HCl. What's the name of HCl? Anybody know that one?
Hydrochloric acid.
Hydrochloric acid. So for binary acids, which have fewer elements, it has a longer name. So we do hydro, then the element name, with the ending changed to ic. Now, because it doesn't have oxygen, it's always ic. There's no us in there. So these are the most common ones. These are inorganic acids. We do have one example on your sheet of an organic acid. And notice in these cases, for the inorganic, we start with the hydrogen. That's what's most common, okay? Which of the acids doesn't start with the hydrogen?
Acetic acid.
Acetic acid. So for organic acids, I'm going to lift this up because I know it gets hard. For organic acids, it's going to have a carbon attached to a carbon with 2 oxygens and a hydrogen. So it's Cu. And then this might be attached to something else. So R usually stands for the rest of the molecule. We don't care what that R is. But this is the key part for an organic acid. So the only one you need to worry about is acetic acid, but we use acetic acid all the time. So you really do need to know acetic acid. So most of you can recognize it or recognize acetate in the list, but I think fewer of you could write the formula without having something to look at. So make sure you are learning the formula. Remember, you can also write it as C2H4O2. Usually you will see it this way so we can identify it as an acid. Yeah.
It's got HC2H3O2, and then under that it's got CH3COOH.
Oh, okay. Yeah, so the only reason it's written like that is just to emphasize that it's an acid, but you will almost never see it that way. You will almost always see it this way. Okay. Our next stop is being able to translate words into a chemical equation. So these are some of the symbols that might be part of a chemical equation. Now, is it fair to assume you all know that the left-hand side is the reactants, and then we go to the right-hand side, and that's the products? That's not confusing to anybody? Okay. So if you see a plus, sometimes that is, obviously, sometimes it is with. So I might say sodium reacts with chlorine. So if you see the word with in a sentence, you need to add 2 things together on the same side of the equation. This might be reacts with, that's an obvious one, or reacts. It might be yields. It might be forms. All of those terms can be represented by that arrow. This one doesn't usually happen in the chemical equation. It's sometimes written above or below the arrow. So this one usually means heat. If you have Dr. Hughes for a lab instructor, she will very commonly use that for heat. And then what do these symbols mean? GS and L. Yeah, so that's telling us the phase. And then sometimes you'll see AQ, which stands for aqueous. What do we mean by aqueous? Yeah, it means it's dissolved in water. So not just that there's water somewhere, but it's actually dissolved, which we know means that we have a clear solution. It's not cloudy, it's not opaque, we can see through it. So all of those particles are spread out throughout that water. Okay, so let's try and put this together. Okay, so if we want to translate this to a chemical equation, what am I going to put down for hydrogen gas? H2. Why am I putting H2? Why not just H? Because it's diatomic. So remember, the dark green on here that kind of form a 7, those are diatomic. And there's one dark green up there. Hydrogen's our problem child. It won't behave and be with the other children. It just has to do its own thing, but it's diatomic. Okay, so that means, so we have with. Now don't be fooled by the reacts. We are going to have an arrow, but first we have to have the with, so plus oxygen gas. So is oxygen gas also diatomic? Yeah, it's also in that dark green area. Okay, how am I going to indicate that this is a gas? With a G in parentheses. The arrow is for reacts and for forms, so both there. So we're going to form water, H2O. Now I didn't indicate the phase. If you've had lab this week, you've seen demonstrations where you form gaseous water, it just goes out into the air. You could theoretically have it form liquid water. Okay, let's try something with some ions in it. This is what you're doing next week in lab. Aqueous sodium hydroxide. Oops, got to move the computer. Reacts with aqueous hydrochloric acid. To form liquid water. And aqueous sodium chloride. Okay, so take a second to figure out what that equation's going to be. So, Sam, first thing that you wrote down for this one.
NaOH.
Okay. NaOH. Wait. So what did you put for a phase? If it's up here, it says aqueous, so what was the symbol for aqueous? It's actually AQ. So that's a good one to know, okay, because sodium hydroxide is actually a solid if we don't dissolve it. Okay, moving back, Clara, what do I put after the AQ? Nope. What do I put after the AQ? Plus, very good. Okay, Clara, then what I do? HCl. All right, and then Elise, what do I do after that? The AQ. And then Kennedy, what comes next? A little arrow. All right. Let's see, Colin, what do I have after that? H2O, because I got water. Will, what comes after the water? Not yet? Not yet? An L. There we go. Olivia, what comes next? A plus. Becca, what comes after that? NaCl. And Ian, what comes after that? I'm sorry? Aqueous or AQ, right? I'm not going to write out the whole word. Okay? Try this one over here. And check with people at your table, make sure they're getting the same thing you are. Remember our ion naming rules. This is ionic and this is ionic. This one is covalent, so we have different rules for them. It's a little bit harder than it seems at first. So looking at a chemical equation, you might be thinking, oh yeah, I know exactly what that means. But if you hear it and you have to write it down, it's a little less obvious. All right, so this first one's a little bit tricky. I'm not gonna just go in order, but who thinks they know what this one, the formula is?
CaCO3.
CaCO3. Okay. I think I left off at Trev. What do I put for the phase for CaCO3? I'm sorry? Yeah, so is it a solid, liquid, or a gas? It's a solid, so what am I gonna put in parentheses? Yep, there we go. All right, Charlie, what's next?
Arrow.
Arrow? Don't I have to add something? Sometimes there's only one reactant, and in this case, it says it decomposes, so it doesn't say it's reacting with, there's no with in there, so yeah, you're correct. Sorry, I didn't mean to scare you. Okay, Sydney, what comes after the arrow? Okay, so we're at this chemical. So what do you think the first part of the chemical is? Ca. And calcium has a +2 charge. And then what's going to be for the oxide? What do you think? Gut reaction. Oxide's going to be pick a letter of the alphabet.
Oh, yeah.
There we go. Okay. So oxide is a -2. Do I need any numbers in here? Or does it balance on its own? With a +2 and a -2. Yeah, it's balanced. Very good. All right, Alex, phase here. All right. John, what's next? Plus, so we have an and here. And then you get to do the last two parts there, Kelly.
CO2. Yes.
And the phase is gas. Okay? So your homework assignment will help you practice translating those things. In your lab this week, you're going to be doing some reactions and you're going to have to kind of think about it in reverse. What am I putting in the test tube? The things that I'm putting in the test tube go before the arrow. The things that I'm observing come after the arrow. Okay? All right, next we are going to look at balancing equations. How many of you have done balancing equations before? How many of you think balancing equations is hard? Okay, so I'm gonna go kind of rapidly through this, and we'll do more examples on Friday, but because we have these types of reactions in lab, I want you to kind of see this. Okay, balancing equation. First, I'm going to go through a set of rules we have to follow. There are 3 rules. Our first rule, and then I'm going to use the formation of water as an example. The first rule is if we have an equation we have to balance, you're not allowed to add any new chemicals or take away. So if I say balance an equation, you got to balance it with what's there, okay? So I might look at this and say, oh, I just need an extra O and put an O there. That's not allowed, okay? My second rule, I don't know why I circled that, it's not like it's extra important or anything, is that you are not allowed to change the subscripts on any of the chemicals. So for example, you might say, oh, well, I have 2 hydrogens, 2 oxygens, let me just put a 2 here. That should solve everything. But now instead of forming water, what am I forming? That's one you used in the last part of lab. We had lab yesterday.
Oh, that, what was that, yellow stuff?
It turned yellow. It was colorless to begin with.
Yeah. That's
So it's peroxide. So hydrogen peroxide is very different from water. If you have concentrated hydrogen peroxide, it can burn your skin. The kind that you might have in your bathroom at home, you might use it to clean cuts and stuff. Very different. So we can't do this. So I'm going to put an X through that. Nope, not allowed. So what are you allowed to do? You can change the coefficients. Those are the big numbers. All right, so all I can do is put numbers in front of these things. Now, without the numbers, I have an invisible 1, so remember that that's there. So since I need 2 oxygens, I'm going to put a 2 over here. And that means I've got a total of 4 hydrogens. So I need a 2 over here to give me 4 hydrogens. Now the 2, the big 2, the coefficient, sees the whole molecule. It's big enough that it applies to everything in the molecule, okay? The little 2, the subscript, is small. It only sees the element it's right next to. All right, so now I have 4 hydrogens and 2 oxygens, and I have 4 hydrogens and 2 oxygens, okay? So that's kind of a guess and check method, which is fine if that works for you, but a method that can be a little bit more consistent is going to involve some steps. Some things that you can do, any method that you do, is you can write out the number of atoms of each element. So for example, I could say, okay, here 2 times 2 is 4 hydrogens and 2 oxygens, and on this side, I have 2 times 2 is 4 hydrogens, and 2 times 1 is 2 oxygens. So I can just check to make sure they're the same. Sometimes it's helpful to put like a line in between the products and the reactants where the arrow is, just so you keep track of what side things are on, okay? It might be helpful to draw the molecules. So if you are having trouble kind of seeing how many are there, maybe draw it out. You don't have to, I'm not gonna check for that, but if that's helpful, you can do that. Okay, so the first thing that I would do is save something for last. So if I see any pure element, I'm gonna save it for last, because if I have a pure element, I can change its number without changing other elements. I'm gonna start with an element that appears only once on each side. So let's say I have CH4 plus O2 forming CO2 plus H2O. Is that all on the screen? All right, so I'm not going to use oxygen. I'm going to save that for last. And on this side, oxygen appears in two places. So I don't want to do oxygen right away. So I can start with carbon. All right, and then, so if I'm starting with carbon, I'm just going to change the coefficient of one of the chemicals so that they match up on both sides. So here I have one carbon, here I have one carbon. Do I need to change a coefficient? No, I'm good. Here I have 4 hydrogens, and here I have 2 hydrogens. So do I need to change something? Yeah, so what am I going to put in front of 1? 2. Okay, so now I have 1 carbon on each side. I have 4 hydrogens on each side. I just changed this side, so I'm going to count the oxygens on this side. I have 2 plus 2, 4 oxygens here. So in order to get 4 oxygens on this side, what do I have to do? I've got to put a 2 in front of my oxygen, which I didn't leave room for, so I'm going to move it over. 2 oxygens. Okay. So we're going to balance each element. By changing coefficients on one side. All right, so now you may end up with what I call an even-odd conflict. So if I multiply an even number by anything, I'm going to get an even number. So 2 times 3 is 6, 6 is even. 2 times 2 is 4, that's even. But if I multiply an odd number by an odd number, I get an odd number. What does that mean? That means that in the case of oxygen, which has a 2 here, I will always have an even number of oxygens on that side. But over here with the water, I might have an odd number. Okay, so if I go through these steps and then I find, man, one side I've got odd numbers and one side I've got even numbers, then I run into an even odd conflict. So let's say I have, instead of methane, I have ethane. Anytime I burn a hydrocarbon, I'm going to get carbon dioxide and water. So there's all kinds of chemicals. Okay, so my first thing says I'm not going to do oxygen. It appears in 2 places here, so I'm going to hold off on that. I'm going to do the carbon. So am I gonna change the number here? No, I'm gonna change it on the other side to a 2. That gives me 2 carbons. All right, I have 6 hydrogens, so what do I need to do over here?
And put a 3
A 3.
there.
Okay, so now I have 6 hydrogens. And then over here, I have 4 oxygens plus 3 is 7. But this requires me to have an even number. Okay, so that's my even odd conflict. So once I run into that, then I'm going to say, okay, let's double everything. Okay, so now I'm going to make this a 2. I'm going to skip this one because I haven't balanced it yet. I'm going to make this a 4. And I'm going to make this a 6. So this is now 4 carbons and 12 hydrogens. Right? So there's 4 carbons, there's 12 hydrogens. Now, on this side, I have 6 oxygens plus 8 oxygens is 14. So what do I need to do over here?
Put a 7.
Put a 7. Okay? That's that. Okay, very quickly, types of reactions. So usually when this is taught as if there are either 4 or 5 different kinds. It really depends on how you're organizing the types of reactions. So I'm going to look at them in some different ways. I'm not going to be able to get to them all today. But the first thing I'm going to look at is double displacement. There are 2 types of double displacement. You will recognize these because you will have 2 ionic compounds or acids. Okay? So in a double displacement, you're going to swap the cations, that's the positive ones, they appear first, or hydrogen, which is also a cation, but sometimes we don't think of that. So if I had, in the example that I put over there, NaOH plus HCl, this is a cation and this is a cation, I'm going to swap those. So if I'm trying to predict what the result of that is, I'm just going to switch those. So H with the OH plus Na with the Cl. Okay, well, HOH, if I were to simplify that, is really just H2O, right? So in this case, this is what's called neutralization. We could also have just ions with no acids, in which case we would have a precipitation reaction. Precipitation involves 2 sets of ions. Single displacement involves 1 ionic plus 1 element. Okay, so we might have HCl plus a metal, like magnesium. In which case, we are going to swap the cation for the element. So what that means is, this is the pure element, so I'm going to have Mg combined with the Cl. What's the formula of MgCl? Charge on Mg is 2, charge on Cl is -1, so how many chlorines do I need? 2. And then this, which was the cation, is now going to be an element. but I know it's not hydrogen by itself because hydrogen's a diatomic. Okay. Your other ones, decomposition, you only have one reactant. And synthesis, you only have one product. And I'll get to the fun part.